My name is Qingkai Kong. I come from Berkeley Seismological Lab. And we know that in today's smartphones, and we have like accelerometers and other sensors like a magnetometer, gyroscope. And these sensors actually can be used to detect the earthquake. This is actually our goal. Actually, we want to use the accelerometers right now in the smartphones to detect the earthquake. Well, so in order to set up a network comprised by the smartphones, there are a lot of questions need to be addressed. So today I will give this presentation slightly different. I will just try to answer 5 questions from this project, and then from these 5 questions, you will have a better view of this project. And then I will end this with this presentation with an advertisement at the last. Okay. So the question 1 is, can we record an earthquake on a smartphone? Well, probably you have already know the answer, because this is all reviews. So, well, yes. The answer is yes. Well, this is actually the record from the South Napa earthquake. You will say, wow, what's this? Looks messy. Well, this is the 3 components from one of the smartphones. Actually, I was carried that afternoon. You can see that it's starting at 4 o'clock, and this messy waveforms here actually is recorded by my my own activities like walking, running, driving, and also eating with my friends. And then comes here, you can see that there's some spikes, but the shaking, you can see the shaking amplitude is relatively small. And also, actually this is at night. I put the phone on my desk, and then someone might touch my phone, someone might touch my desk. You can see these spikes. But where is the earthquake? Well, you can see this red box here. If you see very carefully, actually the earthquake is here. I think some people with good eyes can see that one. But if we zoom in, so this is actually the record. We recorded on a Samsung Galaxy S4, which I actually put freely on my desk. And you can see the 2 horizontal components. By the way, I actually oriented the phone to the east-west component and north-south component before this earthquake, which is very lucky, so I don't need to rotate it. So yeah, now you can see this is the 2 horizontal components, and that's the vertical components. So we demonstrated that here that we can actually record an earthquake with magnitude 6 earthquake at Berkeley here. It's about 38 kilometers away from the epicenter. Okay. So now we should ask ourselves another question. So we can record an earthquake, but what kind of earthquake can we record? How smaller the earthquake we can record? In order to answer this question, we did some noise floor test, which actually is we basically tested the phone here to record the noise for about 1 month, and then we try to find the noise level of the phone itself. So an easy explanation is that, so if I have a signal above this noise level of the phones, then we can see actually this is real signals. But if it's buried, if it's below the noise floor, then it's buried into the noise. So this is a key figure from this test. And you can see, okay, let me see whether I can drop this down a little bit. Okay, so the horizontal component actually is frequency, and the top bar here showing you the period here. And this is the vertical component is the spectral amplitude in dB. And the 2 green lines at the bottom here is the high noise floor of the Earth and the no noise floor of the Earth. And also these dotted lines with the number here, this is the earthquakes within 10 kilometers. By the way, this data set, this earthquake data set is from John Clinton here, and thanks for the data set. And these colorful lines, which is beautiful, and this is the noise floors of the phones. You will see, wow, these noise floors are quite high. And yes, this is the current status of the smartphone. They are low cost, and the quantity is very low. And the colors showing here actually is the release date of these noise floors, of these phones actually. With the cold color actually released relatively earlier and the warm color released more recently. And you can see that we can take 2 points from this plot. The first one is with the earliest smartphone, this one, the 2011, 2010, we can see the earthquake actually above magnitude 5 within 10 kilometers. But with the latest one, the Samsung Galaxy S4, this one here, actually we are starting to see the magnitude at 3.5 at 10 kilometers. So this is the current status. And then another point is that, so these noise floors actually divided into 2 parts and 2 groups. You can see top group and bottom group. And the top group is mostly the cold color noise floors, and these are more like warm colors. So this is telling us that actually the quality of the accelerometers in the smartphones actually is getting better. It's improved. So we hope that in the future there's a good chance that these noise floors actually can be dropped somewhere between here, and there's like a HP MIMO sensor to work as a reference here. Maybe we can starting to see magnitude 2 or magnitude even 1 from these smartphones. Okay, so now we understand that we can record with the current smartphone, we can record the earthquake within 10 kilometers larger than magnitude 3.5. So the other question is, if we have large shakings, what's the behavior of these phones? Whether these phones can behave good or not during large shakings. Well, so here showing you the test actually we did here, the shake table test. We did a series of shake table tests with like sine waves, earthquake waves we converted from the strong motion records. And you can see that, so the blue traces here actually is from the reference accelerometer which are attached on the table. And the right traces here is from the phone actually bolted on the shake table. You can see that actually they are matching quite well, except for some like very minor like discrepancies. And this is telling us that if you bolt your phone on the ground, will be like you can record very nice waveforms. But actually no one wants to do that. So yeah, in reality, so the smartphones actually, you carry your smartphone walking with you, and during the night you put on the desk, put on your bed. So this is what we see actually from the shake table test, this black curve here. And you can see that it's starting to record the waveform, actually matching the table data quite well. And at a certain point, around like 0.3 G here, it's starting to clip. The amplitude is starting to clip. The reason for that is the smartphone actually when the shake table moves, and then the smartphone starting to sliding when the amplitude of the movement actually exceeds a certain threshold. So this threshold actually, of course, it depends on the material and other factors, but this is to help us to understand that the moving phone, in reality, what we need to think about this when we develop algorithms. Okay, but this is telling us that, so the quality of the accelerometers inside the smartphones actually can record large shakings, but then you need to do some like, you need to do some special treatment about that. So we are actually working on that. And the question 4 is, well, we can see all these things, but then whether we can see the P waves from these smartphone records, and if we can see what's the distance range we can see these P waves. Well, to be honest, we are now very close to have this network, but unfortunately, we don't have this network before the South Napa earthquake. Then otherwise, we will have a very nice network. But here, I did a simulated network, which Basically, I downloaded all the strong motion data in Bay Area, including the nightquake data, and during the South Napa earthquake. And you can see these like blue triangles actually is the stations from the Bay Area, and this one is the epicenter. Well, what I did actually is I used the smartphone noise. I superimposed these noises onto these like strong motion records and assume that this is actually from the smartphone, from a smartphone network. This is, of course, the ideal situation. This is assumed like the smartphone is bolted on the ground, but this gives us the sense like whether we can see the P waves from these records. And you can see this is a record section plot with the sorted by the distance, and the right traces here actually is the raw waveform data from the strong motion stations, and the blue ones is the ones actually I added the noise to these stations. And you can see that, so up to about 40 kilometers, so the blue traces actually is, you barely can see these blue traces. And then up to 50 kilometers, you can see that these blue traces is more dominated. And so close, within 50 kilometers, this means that you can see the P wave portion actually quite well from these records, but all the P wave portion actually is buried into the noise up, above the 50 kilometers. So this is the results we got from this one. And if we zoom in to have a better view of it, so you can see the P wave portion actually quite clear from up to like 40 kilometers. And then to the 50 kilometers, you can see that the noise of the smartphones is starting to dominate the first initial part of this network. Okay, and then the next one, actually, so we think that, oh, if we just apply a simple STA-LTA algorithm on these data sets, so what will happen? So the right dots here, these very linear dots here actually showing us the raw data from this from the strong motion data, and this is the trigger. This is actually sorted by the distance, and this is the trigger time since the origin time using a simple STA-LTA algorithm. You can see that these right dots mostly triggered at the P wave. But for the smartphone noise, if we add the smartphone noise, and you can see, actually here, you can't see quite clear, but it's actually around 40 kilometers. You can see most of this is still triggered on P wave, but after that, then it's starting to have another trend to trigger at the S wave and the surface wave. So this is the case. If you go back to here, and you will see that, so at about 50 kilometers, you can't see P wave, and also but the good thing is at 130 kilometers, you can still see the largest shaking at this point. Okay, so the last question, okay, I still have time, right? A little bit. Okay, the last question is whether we can recognize earthquakes. You might ask, like, we carry the phone with us, so there's lots of human noises, how we recognize the earthquakes. Well, in order to answer this question, we are developing some apps, we are developing some algorithms, but I don't have time to show the details. I want to show a demo here. So this is my user display, and this is showing whether I'm standing, running, or walking. And the vertical bar showing the probability of my activity. Okay, if I'm now walking, it's showing I'm now walking. And if I'm running, it's showing I'm running. And if I'm walking, and if I'm standing. Well, how this works, actually we developed the algorithm, try to recognize the different human activities. This is actually from my smartphone in my pocket. And it's streaming the acceleration data back to my Mac and processed the data actually here. And this is showing that we actually have the ability to recognize the earthquakes, to recognize different human activities. Okay, let's go back here. Okay, I promised you I will give you an advertisement at the last. So, yes, we are now ready to distribute the app. We have already uploaded the app to the Google Play. So if you have an Android phone, sorry for the iPhone users, it's not ready for you right now. So if you have the Android phone, you can contact with me, and I can register you as a beta tester, and you can help us to record the signal. This is our app. So this is the smartphone app we call MyShake. We developed here. Basically, it can uploading data from the smartphone, trigger from like large shakings, and also it can also triggered by our server, so we can trigger the phones within one distance from like one location. So anyway, if you are interested in becoming a beta tester and contribute to this smartphone network, contact with me here. Okay, thank you. I will leave it to you.
A quick question. Tom.
How are you handling privacy issues?
Yeah, that's a very good question. Actually, this privacy issue is always the question for this project. Actually, we are now thinking about this, and also we are developing some triggering algorithms actually running on the phone. So we only we require the phone keep stationary for like 1 minute, and before that we won't record any data. And then after this stationary, and then we will monitoring the acceleration. But at this moment we are still not uploading the data to our server. We didn't touch any of the private data from the user. When there's an earthquake occurs, it triggers our phones. We will only record, say, like 1 minute or 2 minutes data and extract the location at this time point. So this way, we think that actually we are extract as fewer data as possible, so that we can do our best to keep the privacy of the users.
I'm sure UCB actually has privacy policies, and have you checked with the university to make sure that you're compatible with them? Believe me, we did, and it's very complicated.
Okay. Yeah, that's a good question. I think that's a good comment. We will check.
How do you timestamp the time series? And what's the accuracy of whatever method you use?
So the timestamp? Yes. So the timestamp, actually, we are extracted from the smartphones, and also we synchronize so most of the smartphones these days can synchronize based on the network clock. And to be honest, we tested that, but I forgot to put the figure here. If you are interested, I can show you later, like the time drift across different phones. Yeah.
I just want to add a comment. So yesterday, people talking about how complicated it is to educate the public when people are receiving a warning. I think this will be a useful tool that you can actually specify the kind of warnings for different type of people, whether they are lying on the bed or driving a car. Then your cell phone apps can tell them to do what exactly they need to do.
Yeah, that's a good comment.
All right, thank you. We need to move on.